Hi everyone, I'm Yui Takeshita, and then so I'm going to give a quick intro talk to BGC Argo and GO-BGC in general, and then some updates that we have had in our program since about 2 years ago when we ran a virtual science workshop. And so I want to mention that, before we start, I want to mention that, acknowledge the funders for this workshop. So this workshop is supported by the Global Ocean Biogeochemistry Array, or GO-BGC, which is funded by National Science Foundation, and then the US OCB Ocean Carbon and Biogeochemistry supported a lot of the travel funds as well. So very special thanks to them. And also, I want to acknowledge all of these additional, what we are really presenting today really builds on biogeochemical Argo, which is an international effort. It also builds on the core Argo project that has been going on for decades, and dozens if not hundreds of people's contributions over the many decades, and the funding agencies that really have supported the technology development, the array implementation, the science, et cetera, for all this. So this is really we are building on a culmination of decades and many people's efforts, and that'll kind of be a theme I'll be coming back to a couple of times in this talk. So yeah, thanks to everyone who have supported our work so far. And so, okay, so as I mentioned, 2 years ago, we did a virtual, this was in the era of COVID, and so we did a virtual science workshop for GO-BGC, building a community of biogeochemistry float data users. All the talks are archived on YouTube. So GO-BGC has its own channel, 97 subscribers. We're basically viral in the science community, but we have a whole playlist of all the talks. So this workshop had a series of pre-recorded, in-depth talks about sensor technology, float deployment logistics, shipboard measurements, data system, things like that. And then we also had summary talks during the talk, and then a lot of discussion. So if you are interested in any of those topics, I will refer you to this this YouTube channel. And we're really not going to cover that today because we kind of did that and we didn't want to repeat the same thing. So today we were just going to give a kind of a brief intro and then just updates since we gave us updates from 2 years ago here. But yeah, if you're bored, just go and watch it. Lots of good information there. So biogeochemical Argo is, so we're trying to build a global array of profiling flows equipped with biogeochemical sensors, and the 6 scalable sensors that exist that are commercially available have proven to be robust and can be deployed in dozens or even hundreds of floats is oxygen, nitrate, pH, chlorophyll A fluorescence, backscatter, so this is a proxy for POC in the open ocean, and irradiance, downlink irradiance, so that's light levels. So those sensors form the core of BGC Argo. And so BGC Argo is a component of one Argo. So this is the new vision for Argo as a program in general. So over the next 10 years, the next phase of Argo is to combine the 3 different branches, the core Argo, which is the the program that has been going on for decades and really has revolutionized how we study the ocean, the temperature and salinity profiles and the 2,000 meters. Deep floats, which are profiling floats that can profile the whole ocean depth, so down to, and they actually sit on the bottom of the ocean. And then 1,000 biogeochemical floats. And then so this one Argo array, the target is that it will form an array composed of these 3 types of floats with a global coverage, and increasing the density in these green areas, which are areas that basically need more floats in order to get the resolution of the measurements that we need. And then the basis for 1,000 floats is explained in this biogeochemical Argo science and implementation plan. I'll come back to this in a little bit, but that array size of 1,000 floats was determined through a variety of simulations and decorrelation length scale calculations. And so focusing on BGC Argo, because that's why we are here, this is a hypothetical array of 1,000 floats. So if we had 1,000 BGC floats distributed evenly across the globe, this is what it would look like. And Rue already showed this, but this is where we are today, and the floats, the symbols are a little bit bigger, so it makes it look a little better, but but we're doing pretty good. There are 545 operational floats. This includes any float that has a biogeochemical sensor on it. So a lot of them only have oxygen sensors, but 310 of them have 4+ parameters. So we're about a third of the array that we want to implement, and then 43 over 6 parameters. And that's particularly exciting because the 6-parameter float was, initially when we started GO-BGC, they didn't really exist. So 3 years ago, you couldn't buy a 6-parameter float, but now the float, the manufacturers, the technologies have evolved so that people can just buy 6-parameter floats. And then the more sensors you can put on a single float, the more effective they are, because it's you get more parameters. And by co-locating multiple measurements, you get to do analyses that you really can't do if you have 2 floats with two different like with 3 here and 3 here. You just have all these mismatches that make the data interpretation quite tricky. So having all 6 sensors on a single float really improves the scientific utility. On the next slide. Oh yeah. So before we go, I have a quiz. What do you think the first biogeochemical sensor was on a float? Oxygen. I think almost everyone will say oxygen. You can't say it can because I know you know the answer. You actually told me the answer. It was actually a radiometer. 2000. Greg Mitchell and Jeff Sherman wrote this report. It was a K-SOLO float. And then so SOLO is a profiling float developed at Scripps, and they put a downwelling radiometer, optical irradiance sensor right here. And I forget where they deployed it, but it was out for about 150 days. They created, so this is a profile of temperature, and this is your log of irradiance here, so you get a linear light attenuation. So they deployed it over spring bloom, I forget where, but anyway, so as you can see the attenuation go down as stratification and the bloom happens. So that's the first BGC float. But yeah, and then so so what I was going to mention was growing a global array really does take decades of work and a lot of contribution from people. So I'm going to go through the history of kind of how, a very brief history of how we got to today's stage in GO-BGC. So it starts with the K-SOLO float. Shortly afterwards, the first oxygen sensor, Seabird 43, Reiser and Johnson. So that was deployed near Hawaii in 2002. 2003, shortly after, the first Ondera Opto. So that's kind of the more classic the standard oxygen sensor on floats now. That was deployed in the North Atlantic. I think Corson right out 2004. That's The Ocean Takes a Deep Breath, another seminal paper. 2004, Emmanuel Boss deployed biooptics, so FLBB, so chlorophyll fluorescence and backscatter, and capture seasonal cycles of these biooptical signatures. 2007, the first nitrate sensor out of Ken Johnson's lab, again in Steve Reiser. The first ISIS nitrate on floats. And then so you can see that this decade really was a lot of people putting on biogeochemical sensors on floats, and kind of proving their utility, how robust they are, what kind of data interpretation you can do, and kind of building this building science project from on a project by project basis. And so these results were really promising. We got people excited. And around the same time, 3 separate meetings that were really instrumental in creating and getting community thinking about a global array happened. And then so 2007, the Argo Oxygen Plan, led by Nikki Gruber. So they wrote a white paper. I remember reading this in grad school and being really blown away by it. And then so they said, what can we do if the Argo array had oxygen sensors on it? And then so they had a lot of great scientific potential and justification of why such an array would be really useful. Ocean Obs 2009, I forget where, held in Venice, Italy. So Hervé Cluster wrote this report on biooptical sensors and profiling floats in an array. There were several others. I wasn't there, but people tell me there were several other biogeochemical float kind of working groups there. And then USOCB hosted a workshop in April 2009, which led to this report. If you haven't read it, I think even the conclusion they come to this in this report still hold true today, observing biogeochemical cycles at global scales of profiling floats and gliders. And so this was really, so multiple groups got together and really started thinking about how can we start thinking about an array on regional to global scales. And so one of the conclusions out of all of this is that it was time to kind of start thinking about a regional array rather than just a project by project basis. And that spawned that led to the Southern Ocean Carbon and Climate Observation and Modeling. So the SOCOM project. This is a NSF funded project of polar programs led by Jorge Sarmiento at Princeton University. It started in 2014, and it was a program that really meshed observations from profiling floats and modeling efforts, and also outreach. And so the initial proposal proposed to deploy 200 biogeochemical profiling floats, deployed with 5 sensors, so radiometers were not included in this, in the Southern Ocean. So that was the least observed ocean basin in the world. If any of you haven't been there, you know why. The waves are horrible, the winds are really strong. You don't really want to be there, especially in the wintertime, even in the summertime too. It kind of sucks down there. But now there is an array of profiling floats. There has been a renewal, SOCOM 2, funded through 2024. To date, we have deployed 271 profiling floats in the Southern Ocean through the SOCOM project. There is a SOCOM 3 renewal proposal currently in review. So hopefully this program will continue. But now the Southern Ocean, I think Ken would argue that it went from the least observed ocean basin to one of the best observed ocean basins because of this continuous observations from over hundreds of profiling floats. So, and another thing that SOCOM really demonstrated was that the float technology, the sensor technology, and the data system were capable and robust to be able to sustain a regional array, so hundreds of floats. So there is a huge leap in effort and like logistical challenges that you have to address when you go from one-off, maybe a dozen float array to hundreds of floats. And then so SOCOM demonstrated that was possible. And then based on that, a group of international researchers got together and wrote the Biogeochemical Argo Science and Implementation Plan. So this was written in 2016. And it concluded that for biogeochemical Argo, the target global array is 1,000 floats. And that was based on OSSIs, so observing system simulation experiments. So in a model, you can put in, what if floats were here, what kind of errors would you get on global CO2 fluxes? I think Matt Maslow did a decorrelation length scale experiment, things like that. And then so on average, to look at the various processes that we care about, global deoxygenation, ocean acidification, CO2 fluxes, carbon budgets, primary productivity, biological pump, and all of those, seemed like 1,000 floats were sufficient to significantly reduce the global uncertainty for these key processes that we care about. And the plan called for that the U.S. will contribute half of the array, so 500 floats, and that's kind of what about the proportion that U.S. has contributed to the core Argo array, so kind of taking on that same proportion to BGC Argo. And another key part of that is that data are freely available to the community to use, because that has been the key to success for Argo, and that will be the key to success for BGC Argo. So based on that, we put in a proposal led by Ken Johnson, and the NSF funded the Global Ocean Biogeochemistry Array, or GO-BGC. So this is a mid-scale research infrastructure 2 project, and so this is a new program at NSF. And so we were funded to deploy 500 profiling floats, biogeochemical profiling floats around the world over 5 years. So we are coming to the end of year 3, and so I think it's in November, the end of year 3. And then so far, and the program was always, was designed to ramp up. So initially, University of Washington and Mbari Apex floats, those are the floats we used for the Southern Ocean. So those kind of form the backbone of the GO-BGC array, and then other partners, Hui and Scripps, were going to use other commercially available profiling floats to kind of augment the array, or to fill in the array, and then aiming to get to 125 profiling floats per year. And currently we have deployed 124 GO-BGC floats, and that's the distribution of floats deployed by this program. The Southern Ocean, we have coordinated very closely with the SOCOM project. So SOCOM currently is filling in the Southern Ocean, and the GO-BGC is doing the rest of the world. And all of these floats are 5 or 6 sensor floats. Most of them are 5, but as I will mention in a little bit, hopefully many of them will be 6 soon. And then the partner institutions for this project, Martin Bay Aquarium Research Institute, MBARI, University of Washington, Scripps Institution of Oceanography, Woods Hole, and Princeton University. And so I want to mention that a program like this really takes a village to operate and conduct properly. This is a picture of the executive team, and I'm not going to name everyone here, but so that's just the executive team. And then in addition to that, there is a whole list of people who contribute to this program. And this is a screenshot I could get. There are a lot more names down below here that I couldn't get in one shot. So I just want to make the point that this is a massive effort, and it really is, we cannot do this without every single one of these people's contributions and help to this program. So we were very, very, very grateful for all their contributions. And since this is an infrastructure proposal, the groups that, we are not getting any funding to do the actual science. We were funded to deploy the floats and QC the data and make it available to the public. It's kind of a service for the community, and that's, and what we believe that is really what's needed in oceanography, and to really enable understanding how the ocean is changing, how much CO2 is going into the ocean on a interannual basis. The marine CDR is coming up. Really need this backbone global observing system to really meet the challenges, the societal challenges that we're facing right now. And so it is, we think that it's all critical, and then so that everyone in this room can start using the data and then learn more about the ocean.
Can I just add one thing to that? In the NSF, their metric for people using the data is to send them proposals. So as you think about, your future, NSF says they're willing, able, interested, eager to receive proposals from people to use the data, which is why we're training you.
Yeah, exactly. So that is our So we're equipping you with the tools, exactly what Ruth said, how to use the data, come up with new ideas, and then so that, you can keep using it, because our metric of success, when people that we don't work with, just use the data, publish papers, that is the gold standard for success. So we really hope that happens. And all this data is freely available. We will go through this later today. So the data is available through the Argo GDAC, through SPROF files. And there are 2 open access toolboxes. The one Argo toolbox developed mainly at PMEL, John Sharp, McFrenzel, Nina Busby, there you are, and Andrea Fostander. We'll have tutorials about that. But also the floats that are QC'd through MBARI, through the SOCOM project and GO-BGC. We also have data snapshots. Every three times a year, we go through and do delay mode QC on these floats and make that snapshot available, so you can publish data using a DOI. And for these floats, we derive additional carbon parameters, PCO2, DIC, alkalinity, and POC, so particulate organic carbon, from our backscatter sensors. What was it doing? Oh yeah, so right now we have deployed 123 GO-BGC floats, and then but we also have 57 floats deployment planned. And then so all of these build icons are floats that have cruises assigned to them, and they'll be deployed in the next 6 months. And then so this map is updated weekly, I think, on our website. And then so if you're interested in seeing where future floats will be deployed in the next 6 months or so, this is a good place to go. Just go-bgc.org/array status. Oh, it's not shown. A13.5. I don't know who has followed this saga. This has been a cruise that got canceled 3 times, I think. So 4th time's a charm. Finally, seems like going in January, but we'll start to fill in this hole in the Atlantic. There's also I-8 and I-9 that is pretty much confirmed in 2024 and 25. That'll fill in the Indian Ocean. So we really are filling in the major holes in all the global ocean basins. In addition to the U.S. efforts, the international community is really contributing and gaining momentum in BGC Argo 2. There have been over 250 floats that have been either funding has been secured or proposals are in to try to purchase by all of these institutions or international partners around the world. And so in general, these are the target areas that people the various groups are thinking about deploying. I just kind of guessed made areas based on last year's Argo ADMT, I think. So the point is that the array is growing. International, there's a big international support as well. And so then we went through this, and then so in order to go from here, I want to really echo what Ken said. You took my punchline, Ken, but you know. But yeah, so like so we're working hard to build the array, but like what is really going to sustain the array is people to use the data, right? As Ken mentioned, NSF is expecting proposals. They want proposals. You can put in proposals to NASA to use bioptic and satellite, data and all of that. And then so we really we want to become a critical part of ocean research, so that people can't imagine doing research without BGC Argo, right? And so that's what this is where you all come in, right? And then so we want the community to use the data, spread the gospel, if you will, but tell people, that, because we do still get questions about how good is the data, is it quality control? There's still a lot of, I think, misunderstanding in the community about what the status of the data is. Is it available? Where can I get the, do I have to email the PIs? Like, no, the data is freely available, and so just that kind of simple, communication to the community, I think, will go a far way. And then so we really encourage everyone, like the future. Oh yeah, and then the last thing I want to mention about this, the future of BGC Argo is far from secure. So there's no follow-on funding prospect right now for GO-BGC. So in 2.5 years, there may be no more, funding to deploy at these massive scales, right? And internationally, there are, like Japan, for example, put in a big proposal right now to try to fund a quarter of the one Argo array. But again, nothing is secured, and then so a critical component for, sustaining BGC Argo once we establish it is for people to use the data, and then let the funding agencies see that, people need this critical infrastructure for ocean research and societal challenges. Oh yeah, and then I wanted to quickly end up, how am I doing in time? Okay, so there have been numerous, even this is before the global, array has really been reached. There are still many science papers that have come out. These are just a couple of the, high impact articles that have come out over a couple of past decades. And the number of papers that are published using BGC Argo really have increased over the past couple of years. And then so we're hoping that this, exponential increase will keep increasing. It's not going to go forever, but but that is very encouraging, and this really demonstrates the utility and the data quality of these floats. And so I kind of wanted to, since this is a top science meeting, I wanted to highlight a couple recent papers, some of my favorites, and to kind of give you an idea of what people are doing with BGC Argo data. So this is Johnson and Biff right here, right? And then so they compile the global oxygen data set from BGC Argo. And then so, so this is really like taking, and Ken will probably touch on this later today, but really, moving away from thinking about a single float by float basis, which is kind of what people have been mainly doing, and thinking from an array perspective. So they're having Rue wrote a series of nice papers showing that with glider data, you can get a diel cycle of oxygen. So oxygen increases during the day and decreases during night during respiration, right? So by compiling a bunch of high frequency profiles, you can actually get a diel cycle. This is, local time, this is respiration, production, and respiration. By looking at the cycle, you can calculate how much productivity is happening in the open ocean. But you can never do this with a float because you have to come up multiple times a day with a single float, right? But then if you have an array of floats that come up, one comes up here, at 2 o'clock, another one comes up at 6 o'clock, and then you aggregate them all together, they show that you can actually get this beautiful diel cycle from multiple floats. And so this is really going from a single float to an array perspective. And then they calculate it, and you can also get depth integrated or depth resolved primary productivity, and so they show that they can do this diel cycle constraint on productivity from the global ocean using profiling floats. And you can see all these gaps in the world, so those are getting filled in. So now this sort of analysis really can get extended too. And then Adam wrote a nice paper on POC, so you can not only do this with oxygen, but POC, there's that yield cycle in POC. So another, array perspective paper. Matt Maslow, by aggregating all of the SOCOM floats, he demonstrated combining with a state estimate, the Southern Ocean state estimate, he calculated the acidification rate in the Southern Ocean, and that's spatially resolved, which makes sense with the physics that we know of the Southern Ocean. So this is the circumpolar deep water coming up to the surface. This should not have a lot of anthropogenic carbons. They saw the least amount of acidification in the area, but then when it interacts with the atmosphere, that's where the acidification happens. And so we're able to resolve acidification, spatially resolve acidification trends in the Southern Ocean based on SOCOM. John Sharp's, this is a paper in review right now, the GO-BGC. What? Congratulations, that's great. So, so this is, as I mentioned, there's a lot of still holes in the Argo array data. And then, so how do you fill in those those gaps? And then, so we can map it using machine learning techniques. And then, so John's paper here showed that you can get a seasonally resolved oxygen inventory from 200 to 1,000 meters of the global ocean. That's in the orange line here. This is the model. You can see they have a nice agreement, but you can see this decline in oxygen content in the global ocean that models have been predicting for a while, and now we have the observations to support that. In the final paper published earlier this year, you can look at iron stress in the Southern Ocean using profiling floats. And so this looks at something called irradiance normalized NPQ. So non-photochemical quenching, so that can happen if it's too much light stress or ion stress. And then, so if you normalize it to how much irradiance or light the phytoplanktons are getting, you can calculate how much ion stress they're experiencing. So they demonstrated by, using some data from the iron enrichment experiments, you see the significant difference in the irradiance normalized NPQ from this is no iron added, iron added. So you can see that there's a significant decrease. Kerguelen is an island that is well known to fertilize the Southern Ocean for the iron that's leached off from the islands. They also show that there is a significant decrease in this irradiance normalized NPQ, demonstrating that you can. So this is a good proxy for iron stress. And then what they can do is now go back 20 years, almost 30 years, and see how the iron stress levels are changing over the years. And so you can, by combining ship and float data, you can get this long-term trend of iron stress in the ocean. So anyways, those are my favorites. I hope everyone has their favorites, favorite science papers as well, but, and give you a flavor for what's being done. And I wanted to end this section with that we are hosting, OCB is hosting quarterly webinars through GO-BGC. And so we are, basically each seminar has kind of a theme, and we're inviting 2 to 3 speakers. And so we usually get about 100 participants and in these webinars, all recorded on YouTube as well. So if you have any ideas, themes that you would want us to do, or if you want to co-host one, right? That means you're reaching out to potential speakers and then try to, it's not that much work, but yeah, come talk to us. The organizing people, so John's been very active, Yibin, Allison Rue, So anyways, yeah, come talk to us, and then, yes, I think that's a fun, and I'll put that sign up link for people who aren't on their newsletter. We'll put it in the Slack. Or remind me to be so fun. And I can move on to program updates next. I'm going to take a pause. Any questions, concerns, thoughts? Yes.
A question is kind of like a broader logistical thing. So you talked about the core cargo and the BGC and everything. And I guess the question that comes to my mind is like, why not just slap as many sensors as possible on everything that everybody's thrown in there? Like, is there a really, really significant cost issue, or like what's the? Yeah.
So the answer is money.
Yeah.
It always is, right? And then so core Argo floats 25K now, 30K, 30K, and then so depending on the manufacturer that you buy, so you get a quote from. So like GO-BGC, because we have, we order, 500, we get quite a discount, but we've heard of international partners. The floats are over $100,000 per float, so it's a 3 to 4 time increase, and their lifetime decreases as well because there's additional power constraints on it. So Core Argo has been flat budgeted for many years, and so they're trying to keep this array going with fewer money, less money, and so we can't cut back into any more. So that's
I figured a decision like that has had more synergy.
But I'll just add that for deep floats, a lot of the sensors, the VGC sensors,
Sure,
haven't been sort of, technologically aren't ready for the deep ocean yet, too. So there's that hurdle to still cross.
the signal to noise ratio is much smaller in the deep ocean. If you have any deoxygenation trend or water mass tracing for oxygen, for example, you really need, they're saying like 1 micromole per kilogram, and that's people working on it, but that's a hard thing. Yes.
Another logistical question, but when we were discussing about the current time to deploy more BGP Argo floats, are all these floats sample up to depth of around 2,000 meters, or do some go all the way deeper?
The BGC Argo is to 2,000 meters, and then because most of the float designs really can only go to 2,000 meters, and as Allison mentioned there, Deep Argo is looking into adding BGC sensors on them. The ones I've heard of are oxygen sensors and biooptics. So POs, backscatter can be useful for looking at benthic turbulence, for example, deep sea mining impact. They dump their, the sediment in the midwaters to see if how big this plume goes and things like that. But yeah.
Just like simple. When you deploy floats, you try to keep the float move less distance, or you deploy a place the drift will go longer distance. How this is declining.
Yeah, so there's a nice tool, Paul Chamberlain developed this as script, so you can look at all the historical float trajectories and see, kind of have a PDF of how they will drift, right? So that definitely goes into the planning, purpose. And then, so right now we are just trying to fill in the holes, right? And then, so ideally, if we can put it in, we know it stays there forever, that's easier to plan, right? And then, but we know that they'll drift away, so then we try to fill in, be strategic about, so a lot of floats, go east-west more north-south, except for in the boundary currents. And so that'll help us plan filling. So if there's a hole over here, we might try to deploy a couple here so that they might float in there. But boundary currents, for example, Gulf Stream, you just throw it in, it will just rip through it. So you just keep throwing them in,
So once the floats are deployed, we don't try to, steer them.
Also, do you ever recover them?
No, we don't. Yeah. Sometimes we do, but vast majority, yeah. Yeah, Mark.
So we're getting back to the question, why not put as many sensors as we can? You mentioned money, obviously, aside from the power issue going on some battery life, is there any, adding more folks from a technical perspective, increase the opportunity for failure? You see that in any of, looking at all the folks that have been employed, it's been an analysis looking at, is it just a matter of just adding more sensors just use more power, or there's other technical issues that can arise?
Adam actually has a nice paper looking at the quality control and the sensor status of all the data in the GDAC. So yes, BGC, each time you add more sensors, right, there is a increased chance of failure. So even if they were all 95% reliable, 95 to the 6th power, all of a sudden becomes much less.
Adding one sensor nowadays is whatever that sensor. Does it influence anything else in the operation?
For the core floats, we have not really seen issues with BGC sensors taking out the whole float, for example, or compromising the CTD. Except for power, this seems like the core mission won't be compromised, in any significant amount. The BGC solos, the newest one from Scripps, you can actually turn off. If a sensor fails, you can turn it off, so then you can conserve power that way as well.
So can you estimate or project the median lifetime now will be for your floats?
Oh yeah, absolutely. Yeah. So right now, I'll get into this. It's anywhere between 150 right now to, that's the Navis's. The new BGC solo is going to be 320 profiles, which is about 6 years. So that's comparable to the Core Argo. But then, price, scalability, that's still a new product. So those are still big challenges for having.
I will mention there's some logistical added difficulties for most of our BGC floats. We deploy them from research vessels primarily, and there's more opportunity for just the plain core floats. There's more opportunities to deploy them from either from commercial shipping or from chartered sailboats or other. It's easier to get them in the water.
That's a good point. So they're a little more fragile. So so because right now like they're so pricey, right? And then so each time we go load them on a ship, we send an engineer to do a dock checkout, and then we can never do that with core floats, right? They just we do that. Oh, we do that with core. Never mind, we do that. Not all groups do that though.
No.
Yeah, but UW scripts do. Yeah. So I guess but like it does. You can't just do it off any ships of opportunity.
I mean, so basically, the sensors will fail, but they don't take the float out. So the float still operates. It just may not have the pH may be dead.
The electronic feedback, not knowing about the guts of these things.
Yeah.
We haven't seen the salinity or temperature measurements be compromised from sensor failures.
And we do usually try to design them, so that one failure doesn't take out the other data streams as much as we can.
Does it make a difference that the sensor, we have a design where the sensor body is inside, the float body is hanging off the side?
No, that's not. It's more on the firmware and like sort of integration side.
Are you guys as sure as the core article about the sampling program? Like in terms of sample rate and yes?
Every single BGC float is a core Argo float. And that is the vision of one Argo, right? And we're all one program, right? And then the essential mission, the core of the mission is core Argo, right? Yeah, so, yeah.
Because the data in order for this to be a sustainable program, the BGC floats need to contribute TMS data, and have a reasonable lifetime.
And we do, so Allison will go into this too, so there are, users for core Argo, right, that have been using it for decades now, and then to not, by adding different, more data to it, different, data formats, like to prevent it being, for them to have to change anything, we have the core Argo, every BGC flow will create like a core Argo file and then a synthetic profile, SPROF, which is the BGC side of things, so it doesn't compromise the core Argo operation. So yeah, that's definitely something that we consider.
For relatively shallower areas like continental shelves, can you park BGC on those?
Sometimes we just deployed 5 floats in the Ross shelf, yeah, right? And then so that was in Antarctica, and so those, so that was an accidental experiment. So a couple years ago, someone, we were supposed to deploy at 3,000 meters. Yeah, but it was at 300 meters, and we're like, oh crap, that's dead. But it survived. They, just parked on the bottom, and it made these beautiful underice profiles.
I don't want to take from the easy layers.
Yeah, exactly. So
not damage to the sensors, or depending on the sensor.
It is definitely a higher risk endeavor, right? So we do not try to do that. We got supplemental funding to deploy more of those, but that's not something that we. But there are some floats. NKE, I think, makes some that are designed to park in the continental shelf, but I haven't really seen those really get deployed in long-term use. Gliders are a good option for continental shelf.
But not here.
What?
But gliders, at least in Southern Ocean, you keep running me around. So there are 5 now in front of the Ross ice shelf. Take the whole 5 sensor suite, BGC sensors, hopefully fill it.
It's under that, so we'll hear back next year.
And this might be something we'll get into later as this goes on, but I'm wondering about sensor calibration. I'm thinking of these shipboard measurements for the oxygen, doing like titrations, like all the way along. That's obviously not possible for these. So is there a way that how do you deal with that? Is that just like we accept the uncertainty, or like is there some kind of correction, or like what?
Yeah, we put in a significant amount of effort to that, and so so we covered this in detail in the last workshop. But briefly, so oxygen sensors, Each time it comes up to the surface, it can do an air calibration because we know what the partial pressure of oxygen is in the atmosphere, and these sensors can measure air. So that's how we get a calibration, and we think that if you calibrate it that way, we can get long-term drift as well. That's good to about 1%. And then for pH and nitrate, we use deep reference fields. And then there are algorithms, global algorithms developed by Brendan Carter, Kenyon B, Henry Bidding, and Raphael. Anyway, so that you can, if you have temperature, salinity, oxygen, and location, you can predict what nitrate and pH are at 1,500 meters, like very accurately. And then so each time a float goes out to that depth, we can calculate what the float measures versus what the reference fields are, and then you adjust it. And then so you can get now drift corrected. And then there are, we know how the sensors drift. So we know that if we correct it at 1,500 meters, we can correct the whole profile. There are various efforts with chlorophyll, doing dark count corrections, and zero offsets and stuff. But yeah.
And the other thing we do is whenever possible, we are collecting the bottle data from deployment cruises, and that is used for validation, not for calibration directly, but we're validating the data sets.
And that's where our uncertainty comes from, So Tanya Maurer had a recent paper, 2021, in Frontiers, I think, that kind of summarizes the validation efforts and the adjustment processes, and then where our uncertainty estimates come from. Yeah, okay. Thank you. Yeah.
We're going to move to the second part.
Second part, yeah, program updates. I'll make this fast because we're out of time. Okay, sorry. Okay, so I'm going to go through sensors, flow technology, and then data access tools. And then so I don't know how many. I think a lot of people have heard about the Honeywell ISPEC production fiasco, if you will. And then so last year, so the Honeywell ISPEC ion sensitive field effect transistor, that's the key sensing technology that enables a pH sensor, the deep sea GeoFed. This is a picture of the deep sea GeoFed on a float head, and the ISPEC is right there. It's about 2 by 3 millimeters. And this chip has been proven to be remarkably stable and great performance for pH measurements. But Honeywell announced that they're going to discontinue the production last June, and this we have known that this was a single source, like failure and weakness in the program. So this is kind of like a nightmare come true moment. And so, but good news is that they have agreed to restart production, and they have restarted production. This was a heroic effort, I would say, by many government agencies, NSF, NOAA, the White House even got involved, and then so we got Honeywell to restart production, and we are receiving chips now, and Seabird has received them, and they have shown us the calibration data, and their performance has not changed. So that's very good news. Long-term, Honeywell is still looking for an external supplier to make these chips, but in the next couple of years, it seems like we're back on track, which is great. But in response to this, single source weakness, we have started looking at alternate pH sensors. So one of them is another supplier of ISPETs, the Lyonics. This is a Netherlands company, and we have received the batch of ISPETs last month. So we are building them into pH sensors right now, and then so that's the chip. It is significantly bigger than the Honeywell. So the Honeywell ISPET has always been a pain to try to seal because you have to put this really custom, super, super tiny O-ring on there, and then so that tends to lead to failures. But this is a bigger one, so we can put a standard O-ring on there. So a preliminary test we did with their evaluation chips seems very promising. So we're hopeful that this would be, and electronically, it should be not electronic, but like data-wise, it should be a drop-in replacement to the current pH system. So the data system won't have to change anything, which is a great bonus. Another one that we're looking into, the pH Opto distributed by Pyroscience. The OEM version of it is called the Pico pH. The data logger version is the Aquafox or Aquafox. And so it has, it's based on fluorescence. And then so this is a sensor response. You have your M member. This is a sigmoid function with the PK and slope. So those are your 4 calibration coefficients. Taylor Worth, where are you? So he's done a ton of work on, trying to develop calibration methods for these. And then so if so each one of these dots is a spec pH measurement, and it's to be calibrated using a range, wide range of pH. You can really, so this is from 0.006 to 0.008, so, or negative 0.06 to 0.08. So you can, these sensors seem to be capable of constraining pH accuracy to about 0.05-ish for the whole pH range. Problem though, so we put these on a spray glider, underwater glider, so these are profiling instruments, and then but the problem is that they're very slow, and then so this is, blue is a descending profile, black is the ascending profile, and you can see there's a big hysteresis, and red is the algorithm predicted pH. We didn't have another pH sensor on this deployment, so you can see that's kind of the correct value, and so you can see there's a big hysteresis, and that's because of response time. So Ellen, she did a series of measurements up in Dalhousie, earlier this year, I think, and then to show that these sensors, this is basically, there's a directional hysteresis as well for response time, ranging from about 200 to 400 seconds. In the field, maybe we're thinking it's 800 seconds. Anyways, too slow for profiling. So we've been working with the manufacturers, and they have developed a fast foil version, a fast response version of it. So they took out the UV protective layer on the optode, and now, so we redeployed this last month, and then showed that the response time is significantly improved. We can actually, measure these, small scale features in the profile, and the pressure, the hysteresis is largely gone from this. So this is very promising. We have 2 of them on profiling floats at UW, and hopefully we will deploy them in the coming weeks and months. So stay tuned on that. Another new sensor, the Seabird 83. So this is an auction optode. So optodes are also kind of slow, but not in the hundreds of seconds, but in the tens of seconds. And so, but they also drift. And then, so as I mentioned, it's critical for accuracy that they can do air calibrations. So you can get the response time by putting in the pump flow stream, which is the Seabird 63, which is shown here, but you can't do an air calibration. And the Aldera here is slower, but you can't do you can do the air calibration. So Seabird 83 is kind of the best of both. So it's in the pump, it's in the outflow of the pump CTD stream, and then so it flows over the sensor and into the ocean. And so that way, but when it comes up to the surface, this plenum drains, and you can do an air calibration. So you kind of get the best of both worlds. And so this was a sensor that was developed under the NOT program with UW, Mbari, and Seabird. And then it's largely just a mechanical redesign, so all the sensing components are the same as Seabird 63, so the performance we expect is similar. And we have 9 of these on profiling floats around the world now, but there's also 3 of these triple oxygen floats where all 3 oxygen sensors were co-deployed on the same profiling float. And so basically, summary, the 83 tends to do, they have better air calibration precision. So this is 1 sigma of the air measurements over time. Blue is the Andera, red is the Seabird 83. So, about 25–30% improvement. And then after you do the air calibration, these 2 sensors agree to better than 1%. So these are across all 3 floats. So it seems like the air calibration quality is comparable to the Anderas. So very good news. So we're going to deploy more of those next year. The response time is substantially faster as well. This is the difference between the 63 and the 83. So they're all in agreement to about a couple micromolar. This is the 63 and Andera, so you can see that there's a large bias in the oxygen. We have also finished actually measuring the response time in the lab. Ben Davis, Peter Wall, Jessica Metter, they made these beautiful measurements. So now we actually have lab-based response time measurements, so we can actually correct them in the field. So I think we're going to slowly transition almost all of our oxygen optics to these sensors. Yeah.
How little oxygen can these new sensors measure?
How low?
How low, yeah.
0. I think the resolution about 0.1. Mark will, we can debate that for, I think he just stepped out. But like in the OMZs, they will read 0, but they do drift. 1 to, kind of has a paper in the Bay of Bengal that shows that some of them drift 1 to 2, but like when it's 0, like you just get this flat line that zeroes out. So. Okay, we are also starting to work with dual channel chlorophyllorometers. We call this the FL2BB. This is a Seabird sensors, next iteration of the FLBBs. And so the motivation is that the chlorophyllorometers right now are exciting. The excitation wavelength is 470 nanometers, and this was largely chosen by LED availability when the sensors were initially developed. And so these are absorption spectra for a variety of chlorophyll and auxiliary pigments. And so this right here is a chlorophyll A absorption spectra, and these are all auxiliary pigments. So you can see chlorophyll A does not absorb at 470. So what we're actually measuring with these fluorometers is not chlorophyll A fluorescence, it's auxiliary pigment fluorescence, right? Yeah, I was surprised when I heard that. If you excite at 435 though, that is at the peak absorption wavelength for chlorophyll A. So we hope, it's notorious, how do you make quantitative measurements from chlorophyll A fluorescence has been a question I think that's been nagging research community for a century or so.
Is it the sensor now on 470?
Yeah. So we have a handful of sensors now. I believe it's a commercially available product now as Seabird, so you can order it if you want. So this is 435, and this is a profile of the two wavelengths. Red is 435, 470. This is deployed off Hawaii, and you can see that they both capture deep focal maximum. There's a little bit of offset at depth, and that's probably CDOM interference because 430 CDOM does for us at a little bit of 435. The Haribay Clusters group has deployed 4 of these sensors in the Atlantic and Indian Ocean. We have deployed 2 in the Pacific. And if you plot up the 470 versus 435, they have these really nice linear relationships, which is encouraging. That means that the 470 measurements are correlated to chlorophyll. But this is just very preliminary. If you just plot, compare the high latitudes to the low latitudes, and this is a 1-to-1 line. There seems to be a relationship, and that could, signify different community composition, nutrient stress, whatever. Another research topic for people to explore that know something about biophysics. I don't know anything. Wavelengths for radiometers. These are the OCR 504s. They've been deployed on a number of profiling floats, but there's a lot of different wavelengths that people have used. But there was a working group, RU was a part of it, and then now the BGC Argo has a report out now, I think, that recommends that that we are going to standardize these wavelengths at 380, 443, 490. So these are kind of the 2 different channels for chlorophyll and 555. And the key outcome or thing was that you can actually calculate PAR from these 3 channels. So you don't need to measure PAR. So we got to ditch PAR and add another channel. Floats. So initially when GO-BGC started, it basically was Apex. So Apex floats, the University of Washington buys the kits from Teledyne, and Bard builds this float, the sensors, pH and nitrate sensors, and then he assembles a float, tests them, and deploys them. The Navis is a Seabird commercially available version, so those are the 2 that were available. But now there is a new float type, BGC Solo 2. This was developed under another NOT program at Scripps. So this is this is a full 6-parameter sensor. So these 2 are 5-parameter sensors. This is a full 6-parameter sensor and capable of doing a lot more profiles. So it is projected to do 320 profiles. And they said that is a conservative estimate, so hopefully they will do more. So that's over 6 years with all these sensors profiling from 2,000 meters. It's in CP mode, if that means anything. That means that the pump is on the whole time for 2,000 meters. You're making 2-meter resolution measurements, except for nitrate. Nitrate still does 70 measurements, I believe, over a profile. And this is now commercially available with MRV, but I will note that they are having supply chain and logistical issues, so there is quite a long lag for these to get delivered right now. Another update, now the Apexes seem to be able to carry an OCR. Initially we thought it was not possible, but we got engineers, did some calculations, and we think we can do it. And then so there is one float deployed off of Hawaii with all 6 sensors. It's working well, except for the chlorophyll channel. I think that was a wrong calibration or something like that, but all the sensors are working. Engineering data looks fine, so we are planning to put, I'm not sure exact number, but more radiometers on floats, on Apex floats next year. And another one, the Navis Nautilus. I wish I had a picture of this, but this is the next generation Navis floats developed by a NOC program. And so this is a Seabird float with all 6 parameters. And the target is designed for 250, but engineers are hoping for something closer to 300 profiles. There's 2 prototype floats that were deployed in Hawaii, and then they're doing daily profiles, and the data look beautiful so far. These are 5 parameters ones. There's going to be another, the 3rd prototype with with the OCR deployed hopefully in November this year. So commercialization timeline is not determined yet, but hopefully in the next year and a half, we'll be able to place a PO for one of these guys. Oh, I'm supposed to cut that out. Data access, there have also been development of the one Argo toolbox, the BGC Argo toolbox was developed for the last workshop, and then PMEL kept updating it, and now it is the one Argo toolbox, works for all floats. And it's in MATLAB and R. Yibin led the R development, John and Armin, I think Nita did the MATLAB part of it. And then and then also Argo Pi is an open access toolbox for Python, and they recently added biogeochemical capabilities. So we will have a tutorial for these toolboxes this afternoon. So, and we recently did a webinar with these new tools for one Argo toolbox and also WebODB. So if has anyone used ODB before? I highly recommend it. It's a really, really powerful program, but now there's a WebODB which has all the SPROF files already loaded into it on the web interface. You don't have to download anything. So this snapshot I think was from June or something like that. And so these are all the SPROF files, and then the interface is exactly the same as the desktop version. And so Reimer Schlitzer, he's the inventor for ODB, so he gave one of the talks for the webinar. And so he can create, I was going to do a live demo, but I thought against that. So you can make, this is the annual cycle, this is a seasonal cycle, oxygen saturation percentage of the North Atlantic, and he made this plot in probably less than 3 or 4 minutes. So this is a really, really powerful tool for data exploration to see what kind of patterns exist around the world. You can derive parameters and all that, so you can play around with it before you go into your more time-intensive coding exercises. So see if there's a signal. Anyways, yeah, please check that out on the webinar. Thank you.